Professor Fratini is a well-known personality of ESAFORM, I would say. He graduated in 1993, had his PhD in 1997 in the University of Palermo. Since yet, he is a full professor of manufacturing in the University of Palermo. He has been the vice rector of for research and submission of this university, and since November 2024 is the director of the Department of Engineering. His scientific activity is mainly focused on numerical modeling of plastic behavior of metal, and also is now starting from a few years to work on solid bonding processes. As you can see, he has also coordinating and is involved in several research projects. And he has a large international recognition, as he has been awarded in 2007 by the CIRP from the Taylor Medal. He's the vice president of, has been the vice president of Italian Association of Manufacturing. He's a fellow of CIRP. He has been the president of North American Manufacturing Research Institution for SMEs. Of course, he was the president of ESAFORM from 2020 to 2024, and is also the new editor-in-chief of the Journal of ESAFORM. It is then a pleasure and honor to leave the stairs to you, Livan. Welcome.
Thank you very much, Mrs. President. It's a great honor and pleasure for me to be here today, and I was very honored to accept your kind invitation. And the only problem is that as you receive such kind of invitation, it means that you're getting older. But nevertheless, it's really an honor to be here today. I will share my screen, and okay. Now you should see my presentation here. Okay.
Yes.
And yeah, and so today I will give you some updates and a brief summary of the activity regarding solid state recycling of alloy chips through friction stir based processes, which we've been carrying out at our lab at the University of Palermo in the last 6-8 years. And I will give you some insights regarding some of these processes with both experimental results and results coming from numerical simulations and numerical models, in order to understand which are the critical aspects of these processes, and in turn, which kind of circularity can be aimed at in order to propose such processes as effective tools even for SMEs, small and medium enterprises, and to reach proper technical readiness levels in order to be applied in the industrial environments. Well, let's try here to move it. Okay. It is well known that in the last years we got industrial emissions that have risen by more than 70% since 2000, and we have an increasing global demand for industrial goods, but also an increasing global demand for metals. And the big five of these players are for sure iron and steel, aluminum, concrete, plastics for sure, but also paper and so on. And they are really critical aspects in the industrial production to be taken into account in order to reduce consumption, but also reduce emissions and obtain benefit and beneficial aspects and benefit from actual production. Well, in the last decade, researchers have turned to several solid-state recycling approaches in terms of traditional remelting approaches in order to reduce energy, save energy, but also save material. And in this way, we have an increase both in the researches and also in the results, in the setup of such kind of solid state processes. It should be observed that in terms of material efficiency, well, remelting processes, traditional remelting recycling processes are characterized by strong metal losses due to oxidation, and which are definitely critical, and properly they are more critical as actual chips are considered. Namely, if we consider bulk scraps, the oxidation losses can be between 1% and 10%. But in turn, if we consider a strong surface to volume ratio in these parts to be recycled, so chips, well, the oxidation losses can be from 10% to 25%. These strongly reduces the material efficiency or the whole efficiency in the remelting process. In turn, in the last 10 to 15 years, in literature, several research groups proposed new processes or somehow revised old processes in which a solid state recycling was proposed. The metals was recovered simply by solid bonding operations. And actually, the solid bonding is activated depending on some critical aspects. For sure, the pressure with whom two metal parts are pressed together, the temperature at which this pressure is given, and the contact time among surfaces. So pressure, temperature, and time are the three critical aspects to be considered in such processes in order to obtain solid bonding. Well, this is well known also in some roll forming operation or multi-stage roll forming operations in which two blanks are pressed together, are laminated together in order to obtain a thicker blank. But this kind of process is also well known, for instance, in complex extrusion processes with porthole die tools, in which the material is first separated and then rebonded in order to obtain complex geometries. In this case, this aspect is taken into account just to recover material, just to recycle materials starting from small pieces, namely chips. Well, in literature, as I've been telling you, we got several cases, starting with ECAP test, for instance, in which this kind of operation actually happens, this kind of phenomenon actually happens. In the last 10 years, and together with the strong increase of the popularity of friction stir welding operations, other processes, friction stir-based processes, have been proposed in literature. And in this case, today I will tell you something about friction stir consolidation and friction stir extrusion, which are operations which can be considered, which can be used in order to carry out solid state recycling operations. And in this way, today we will discuss fundamentally of four aspects and four themes. First of all, I will tell you something about friction stir consolidation operations. Then I will pass to a friction stir extrusion process. We will move to an higher TRL, namely technological readiness level, talking about continuous friction stir extrusion operations. And then we will go to the most recent process introduced in literature, namely friction stir deposition one. Well, as we start with friction stir consolidation, we have to observe that starting from chips, the idea in this process is to put the chips into a chamber, a die, a closed chamber, and to use a vertical tool, a vertical movement tool with a vertical load applied and put in rotation together in order to press the chips and to activate the solid bonding operation. So we have rotation and compression. So we have the tool rotation speed and compression force as process parameters together with the time. And in this way, as the process is carried out, a proper consolidated billet can be obtained under certain conditions, of course. This is a very simple process, but very effective with, of course, some limits. In particular, it should be observed that the process is characterized first by an heterogeneous heat transfer, and I would say an heterogeneous heat generations, since the heat flux is just generated at the interface.
Monsieur, il est 15h17 et nous arrivons alors au gare de Paris-Montparnasse, notre terminus où nous...
Can you turn that off? Thank you very much. So the heat flux is just generated at the interface between the tool and the chips, just on one side, we will see. And it should be observed that in this way, we will have different temperature, but also different process conditions along the height of the billet, which will be consolidated. Furthermore, the process is characterized by a limited material flow during the process. This can be investigated both through numerical models and through experiments with some markers placed in the chips during the process. It should be observed that the material flow is limited, and these would cause some limits in the process in terms of proper bonding. It should be observed in particular that if we consider locally what happens in terms of consolidations in different parts of the transverse section of the billet, which is consolidated, it should be observed that the combination of the heterogeneous heat transfer and the limited material flow during the process leads to some defects, especially at the bottom of the billet. So we observe all along the transverse section of the billet an unconsolidated portion of chips at the bottom of the billet. So the process engineering has to be aimed at the limitation of such zone of imperfect bonding condition of the material in the final billet we will obtain. From the numerical point of view, we can highlight, please the mics, we can, okay. In these images, we can observe the Vickers hardness distribution in the transverse section of the billet, and also the grain size distribution in the same section. It should be observed that these different conditions of bonding during the process actually lead to different local characteristics of the consolidated material. We carried out a huge amount of experiments together with LFT at Erlangen and at the University of Erlangen in Germany, in the research group of Professor Macklin, in which we examined the local mechanical characteristics of the consolidated billets, carrying out some upsetting tests of very small spacements obtained from the consolidated billet in different zones of the billet. And for sure, at highest layers of the billet, we obtained better material characteristics than at the bottom of the billet due to these different conditions of bonding during the process itself. Well, of course, in this case, as in many others, numerical models permit to have an insight in the process and to understand exactly what kind of condition we have during the process, both in terms of material flow, but also in terms of, for instance, temperature distribution, local pressure, and so on. Of course, the numerical model has to be properly tuned, and in this case, we tuned it with comparison between experiments and numerical results in terms of temperature history, but also in terms of local material movement. And this gave us some information. And also, the idea was to apply a huge number of criteria of bonding phenomena proposed in literature, and also some new formulations given by the combination of proper material parameters and material information obtained both from the experiments and from the numerical model. Well, in terms of bonding, the most popular and famous criterion is probably Plata and Pickwick, proposed in 2000, in which it is considered the integral of the history, so of the local pressure and of the material flow. Actually, we used several criteria proposed in literature, and we also gave some new formulation with introducing new parameters in order to have a proper map of what happens during the process and which are the actual conditions which permit to get an effective local bonding of the metals during the process. The criterion which demonstrated a very good behavior in this process was this Plata and Pickwick, a weighted Plata and Pickwick with a new formulation which permitted to have the best overlapping between numerical prediction and experimental validation. Of course, the criteria were tested starting from a collection of experimental data and also a collection of numerical simulations, in particular from the test we derived from the experiments. We derived the local values of Vickers hardness and also the local values of the grain size. And in turn, from the numerical model, we got the information useful in order to carry out the integral calculation of the proposed criteria. Well, in this way, we had this kind of maps. Namely, the last column shows the experimental results in terms of consolidation or not consolidation, giving or introducing a threshold in the local value of the hardness of the consolidated material. And in turn, the first 6 columns gives us the results in terms of the value of the criterion, the threshold of the criterion reached during the process. It should be observed, or at different stages of the processing times. It should be observed that with the criterion number 5, as I told you, the best one, more or less in the evolution of the process, we are able to reproduce the distribution of consolidated, not consolidated in the transverse section of the billet. So this was the most effective criterion in terms of prediction of bonding materials. Well, here we have in turn another step of the investigation we've been carried out, namely the possibility to obtain a billet made by 2 different alloys, 2 different aluminum alloys. So the idea in this case was to combine 2 different kind of chips in order to get a mixed material or a mixed billet with these two alloys. Of course, this is also a possibility, and an interesting issue is to understand how the 2 materials distribute all along the section, and this can be inquired investigating the hardness distribution in the consolidated billet, since the 2 materials are characterized by 2 strongly different values of or average values of Vickers hardness. And this is also interesting in order to have some hybrid or the production of some hybrid billet characterized by two different materials. Well, the idea, of course, in the process is to get the best homogenization of the material in terms of mechanical characteristics as it is consolidated. In order to get this result, we investigated two different ways, two different approaches. The first one is so-called friction stir consolidation multi-step, namely the possibility to interrupt the process, to flip the billet, and to complete the process with the flipped billet in the second part of the process, or to have a mass addiction approach, namely to use the half of the material to carry out a first consolidation, to add the second half of material, and then to carry out the second stage of the consolidation. The other possibility, of course, probably more complex, but more interesting, at least from my side, is to have a more complex fixture in order to carry out the process, and in particular to have an heated backing plate in order to increase the heat flux or to make it more homogeneous all along the section of the billet to be obtained. Well, in the multi-step approach, as you see, the idea at the end was to get a flatter, I would say a flatter trend of the Vickers value from the top to the bottom of the billet. This is the trend, which is quite steep in the single step approach. Both in mass addiction and double-sided, but in particular in mass addiction, we have a definitely flatter trend of the material hardness in the consolidated billet, and this shows as it is possible to improve the mechanical characteristics of the billet itself, just modifying the approach of the process. And it should be observed that even from optical observations, we can see that several defects characterizing the bottom zones, zone 4 in this image, of the consolidated billet in the single step process are avoided in the multi-step microstructure, in which, in this case, no defects are observed and a more homogeneous material is obtained. As the new setup is regarded, here I got some numerical results in terms of temperature, but in terms of strain and density, which are definitely better than the ones of the single stage process. And these are the results in terms of consolidations. Okay, so this is the first approach. It's not perfect, can be improved, but it looks promising. But for sure, friction stir extrusion can be considered even more promising, even if, the first question that a guy working with me told me as we started working on this, but he told me, but the final target are just wires. Yeah, you're right, are just wires, but the production of aluminum alloys is wires all over the world for 80%. 8% of the whole production of wires in aluminum alloys is of the 8% is aimed to get wires. So wire is a good product even for aluminum alloy. It should be observed that in this case, we have a backward extrusion mechanics. So the chips are placed into a chamber and an extrusion tool, an extrusion matrix is pressed against the chips, and it is put in rotation, and an extrusion load is applied. And in this case, in this way, we obtain the consolidation of the chips and a backward extrusion mechanics obtaining the wire as extruded products from the billet into the chamber. Of course, it is a discontinuous process, and the main process parameters are rotation speed, extrusion load, but also extrusion ratio. Since, as we remember, the extrusion ratio definitely determines the mean stress in the middle of the wire in this case, but we would say in the middle of the extruded parts. And so in this way, it is very, very important in order to get proper and effective bonding conditions all along the product section, all along the wire section. Here you can see a process map for this operation, namely at the varying of tool rotating speed and extrusion force, we obtain some different conditions, a sound product, a torque limit of the machine, or hot cracks. Namely, we can't go too much with high values of tool rotating speed and tool force or extrusion force, since otherwise we obtain too large levels of temperature, and in this case we obtain a product characterized by external and extensive crack on the surface, as it is shown in this figure. And of course, also the average grain size is different at the increasing or at the varying of the temperature distribution in the wire during the process. And again, a numerical model was proposed and introduced for this operation. Also for in order to understand the temperature distribution during the process all along the section of the billet, and the extruded wire, but also to properly investigate the material flow actually occurring in the extrusion mechanics during the process itself. And in this way, it was possible to highlight the actual fact that a sort of spiral movement is observed. In this case, here it is shown both with a node tracking approach with the used software, but also with some markers in the experiments. Namely, the material undergoes a proper spiral movement with spires characterized by a pitch, which is strongly dependent on the tool rotating speed, on the extrusion matrix rotating speed. And in this way, at the varying of the rotating speed, but also at the varying of the extrusion ratio, different combination, and in particular different spirals are observed in this kind of movement, in this kind of material flow. And in this case, it was possible also to relate somehow the average grain size in the wire section, in the extruded part section, with the Zener-Holloman parameter of the material during the process. Zener-Holloman is the temperature compensated in strain rate, and it was implemented and calculated in order somehow to predict the evolution of microstructure during the process. And we observed different zones in the wire section, which were, of course, characterized by different values of the Zener-Holloman parameter, and as a consequence, different values of the average grain size during the process. And at the end, the most important thing is that as you observe a different grain size all along the section, but of course, at the varying of the extrusion ratio, you have a strong variation in the bonding condition in the wire section. And in particular, as the extrusion ratio is not so high, you will observe local inconvenient conditions and local ineffective bonding conditions, as you can see here with such green line. And this shows you, or this somehow gives you the possibility to have an insight in the defect observed in the wire as a too low value of the extrusion ratio is used, since a too low level of mean pressure is obtained at the core of the wire itself. But of course, as I told you at the beginning, this is a discontinuous process. And in this way, it is interesting to be investigated and analyzed from the academic point of view, but people working in industry would be more interested in a continuous process. And the idea a couple of years ago 4 years ago, I suppose, was to carry out a machine able to carry out continuous friction stir extrusion operations. In this way, here you see both the actual experimental machine we have, or we carried out, we designed it first and then carried out, and the principle for which the process actually is carried out. Namely, the chips are placed in this hopper, and they are conveyed up to such cochlea, which is put into rotation and actually starts to hit them just for friction, moving all along the fillet of the cochlea. And the chips are then pressed against an extrusion chamber in which a tool, an extrusion die, is found out and put in rotation with another engine of the machine. And in this way, the actual extrusion occurs, and theoretically, a fully continuous process could be obtained or can be obtained. Actually, it should be observed that the addition of chips have to be well done and definitely continuous and stable in order to let the process being really stable and continuous, actually continuous. Should be observed that, as you can see, it works. I mean, it works. It is complex. It is sometimes unstable, but actually it works. And you got a very complex setup of the machine, but also a very complex process engineering, since you have to properly tune the tool rotation speed, so the extrusion matrix rotation speed, the cochlea rotation speed, the applied force by the cochlea, but also some distance in terms, for instance, of the actual height of the extrusion chambers, since such height determines the amount of material which can be contained and pressed just in front the extrusion tool, and so on. It should be observed here, you see the result of one of the experiments, so half a meter, but we obtained even a couple of meters or something like that. But the problem there is to properly maintain the process stable, first of all, with the proper stable addiction of new chips. And again, here you see the transverse section of the wire with the considerations we already carried out for the friction stir extrusion process with several aspects. And yeah, in this case, the numerical model was a challenge, since we have so many bodies, so many different bodies, and so many contact surfaces for which you have to carry out a quite complex and heavy models. And if I go back to my graduation thesis, this would have been a dream to manage such kind of complex numerical simulation. Today is definitely feasible. Today is reachable. And this simulation, this campaign of numerical simulation was carried out just in order to understand which kind of process parameter ranges would have been necessary in order to design the continuous friction stir extrusion machine. And in this way, here you find out the ranges of all the process we used for the design of our machine. And finally, friction stir deposition. This is quite popular in the last years with several applications. The principle is to, for instance, in this simple case, to start from a consumable rod, which is put into rotation and on which an axial force is applied. And in this way, some frictional forces work are produced at the interface between the already deposited layers and the consumable rod. And in this way, some heat flux is generated and a new deposition is obtained with a new layer. Well, just to let you know or to understand what we're talking about, this is what happens during the process. And of course, the results is the considering a single layer, it is very difficult to control the actual deposition in terms of geometry of the deposited layer. And of course, at the end of the deposition, you have to machine, to mill the deposited wall sometimes in order to have or obtain or to get a regular shape of the deposited material. But it is quite interesting and popular in the last years. And this is the obtained results, for which you can observe here at the bottom of the slide a central core of the deposit layer for which no defects are observed, and in terms the lateral, the peripheral zones of the deposited layers for which imperfect bonding conditions are reached, and in this way, even in this simple transverse section, some voids, some macro voids are observed, some defects are observed, and these parts have to be milled, have to be eliminated after the process. And of course, it has to be observed that different process conditions are obtained from the first layer to the last layer, since the first layer, is deposited on cold anvil. In turn, in the other deposition, you will find heat zones and an already heated material. So different conditions, different process conditions are obtained. Well, this deposition process gave the idea and gave the possibility to set up and carry out an actual industrial symbiosis. So in these solid bonding approaches, in order to recycle materials, and in particular to recycle chips, the final idea is to get some new products like billets or wires, which could be reused in industry. So which could be definitely used in a circular approach to carry out something new. Well, here the idea is to use the wires obtained through friction stir extrusion operations in a new deposition process. They could be used, for instance, in welding operations, but here is the idea is to reuse them in order to obtain a proper layer to be deposited on an anvil, or in order to repair, for instance, some surfaces. And here you can see that this kind of approach has been followed in literature with several kind of processes. So friction stir extrusion and additive manufacturing, or simply friction stir deposition, or the WAM approach, and so on. So the idea here is that this kind of process is characterized by a tool with some pins at the end, with plunge into the previously deposited layer or substrate, and in this way a sort of forward extrusion. Look at the bottom here. A sort of forward extrusion is obtained of the deposited layer with a geometry with a sort of T shape of the deposited layer. And the tool pins obtain a sort of fragmentation and at the same time plasticization of the material, in which a new recrystallization phenomena can be obtained. And in this way, at the end, we obtain several layers in such kind of shape, with a nugget zone, so a central zone in which a very strong grain refinement is obtained, so a very strong average grain size reduction all along the section. And in the lateral zones, simple solid bonding zones are obtained, sometimes with some defects eventually. Well, from this kind of deposition, you can carry out local investigation of material characteristics and material behavior, typically through tensile test or hardness test, in order to understand which kind of trend is observed in terms, for instance, of hardness. And as I told you before, we have strongly different conditions from the first layer, in which a totally different temperature boundary is given, and the other layers where already a hot layer are found out as they are deposited. Well, and you can see here that the material characteristics are different from the nugget zones and also from the advancing side and retreating side, considering the deposition as a friction stir based operation from the two sides of the deposited layer. Well, overall, I hope I was not too long. Well, the idea was just to give you an overview of different based processes for which actual recycling of metal chips, in this case aluminum chips, can be carried out, and to give an overview in terms of different approaches and also new trends in terms also of combination of recycling and deposition of material with approaches characterized by solid bonding phenomena, no melting at all, trying to maintain a quite large or quite good level of mechanical characteristics, even at a local level, even in definitely difficult zones of the recycled product, both in terms of billet and in terms of wire. And that's all, I think. Thank you very much.